Imagine you want to walk from point A to point B. Let's say that's a distance of about 1 meter. Well, that's no big deal to walk across that. But we're not going to do it that way. We're going to try and walk this distance in a completely different way. Instead of just striding along, we're going to walk to the halfway points. Instead of just striding to point B, we're going to step halfway to 0.5. Now we'll go to the next halfway point, which is 0.75. And then the next halfway point. And the next halfway point. This is where you need to try and free your mind from the physical world and step into this realm of abstract mathematics. Because what's happening on the left can't continue forever. Putting aside the fact that I could never walk with this level of accuracy, I eventually would just collapse from exhaustion. But what's happening on the right in the mathematical world can continue forever. There are more decimal places here, but I've reached the limit of the software I'm using. I can't show you this process of going all the way to infinity. It's abstract. You have to reason to it with your mind's eye. We can make the number of steps forever larger. We could say this is going to infinity. The big question to answer here is, what is the position going to? Well, it's going to 1. You can see the patterns of 9s stacking up. And imagine that this process continues stacking more and more 9s, well beyond what my computer software can even show you. This goes on forever. There is an important point to be made here. The data is showing a pattern of going to 1. This number 1 is also the exact distance between A and B. This is where we are connecting this infinite process to an exact number. This infinite process will never reach 1. It will never output the number 1. But this number 1 is the exact number that this process is getting forever closer to. So here we go for the first question of the lecture work from my math lab. Here it is. Looking at this new data table, what is the position going to? What number is this pattern going to? Well, if we look at all the 9s stacking on here, 2.99999, and imagine this is going on forever, well, we're approaching and going to the number 3 here. And number 3 is the exact distance we would be trying to walk across here then. So again, this infinite process of getting closer and closer, each number here is approximately 3. Each number in this data table that goes on forever, but it'll never equal 3. It'll always be approximately 3. But the number that this is all getting closer and closer to is the exact number 3. So check this out for question 2. What number is this data table going to? Well, look at all the 9s here stacking up. We always have a 7.4. And then we got all the 9s stacking up. And so this is getting forever and ever closer to the exact number 7.5. So here we have good old x squared. And we're going to deal with every number but the number 2. Number 2 is going to be our area of interest, but we're not going to ever use that number, just like we've been talking about. We're going to approach this number forever. So let's imagine again, we have our points A and B. So we're going to start at A, we're going to walk to B and get forever closer to the number 2. But now we have this function involved. So let's now imagine there's this bar that's being drawn up to the function, and then it's going to go across to the y-axis so we know the output of the function. So we're going to walk across to B, and this bar we're going to push along with us. And it's always going to be giving the output of the function. And here's where we get forever and ever closer to B. We're going to get forever and ever closer to our point of interest, the number 2, but never going to become the number 2. Now the pattern I showed with getting forever and ever closer by going to halfway points, that's only one way you can do it. There's actually many ways you can get forever closer. And a way that's a little bit easier with tables is to just keep stacking on 9s. So again, we're going to get closer and closer to 2. And so for our inputs, we're just going to get stack more and more 9s on there. And if we plug this into the function, then we're going to get this output. And again, we look and we see our inputs. Our inputs are going to the number 2. And if we look at the output data, we can see this output is going to 4. Now, these are the words I've been using so far, but here's where we need to introduce some notation. And we actually don't say going to 2. We say it approaches 2. And this is where we're going to have some new notation in here. Then with the arrow, we would say this is x approaching 2. And approaching specifically means this concept, this idea of getting forever and ever closer. And as far as going to 4, we don't necessarily say that over here either. What we say is the limit is 4. And here's where we got some new notation that is the limit that we're now going to talk about. So what you're used to is function notation, where you just have some function, say x squared, and you look at this and it tells you, oh, I plugged the number 2 in, I get the number 4 out. So with function notation, you plug in one number and you get one number out. That's different with the limit though, because with the limit, we're going to plug in all numbers except our point of interest. So with function notation, you plug your point of interest in, but with the limit, you plug in every number but your point of interest. So let me show this idea graphically. Here's x squared. We're just going to zoom in on it. I'm going to go with our point of interest being 7 this time. So with function notation, you just plug the number 7 in, and you got your output of 49. With the limit, however, what we're going to do now is we're going to approach 7. And we're going to approach 7 from the left. And this approaching from the left has some new notation here. This little minus sign in the superscript. That means specifically we're going to approach 7 from the left. And that's what this signifies. And here's the output of our function then going this way. And we're also going to approach this from the right. And from the right gets the superscript of the plus sign. And again, this means going to the right. We're going to draw up to the function and draw over to see what our output is. And we're going to approach 7 forever. And so we're going to get closer and closer and closer forever and ever and ever. And if these outputs converge, then we'll get a number. Now, this process doesn't always lead to the outputs converging. And so here's an example of that. Let's say our point of interest is 7. And here we have approaching from the left. So approaching from the left gets the minus sign. And we'll also approach this from the right, so that gets the plus sign. And what's important to notice this time is the outputs of approaching from the left and the right. This output is no longer going to converge. It's not going to get closer. Instead, as we approach 7 from the left and the right, the outputs will get farther away from each other. And that's actually not what we want. Ultimately, with most of our calculus stuff, we want this process to converge. But in order to talk about what's converging, we do need to look at these individually. So let's just look at the left side here, this process of approaching from the left. So here's a data table to illustrate that if we approach from the left. And this approaches so quickly, actually, that again, it starts to break the software. So minus 43 means there's 43 zeros before 0.372 there. So this is clearly going to 0, very small number. And we would write this then as the limit as x goes to 7 from the left is 0. Now, if we look at this from the right, we'll approach from the right side now. And here's a data table that illustrates that. Now, notice approaching from the right means we start with numbers that are larger, and then we go to numbers that are smaller and smaller, but they're always larger than 7. That's what approaching from the right means. It means you're choosing numbers that are larger, but then you get closer and closer and closer. And if we look at this data table output, this number is blowing up really high because 10 to the 41 means there's 41 zeros after 269 there. So that's a hugely ginormous number. And that, we would say then, is blowing up to infinity. And so we'd write this then as the limit of this function as x goes to 7 from the left equals infinity. It's going off to infinity, and you can see that on the graph. And these are types of things we can't talk about with algebra. With algebra, if we just plug 7 into this function, we get division by 0, and we just say it's undefined. With using limits, we can start talking about how these ends are breaking apart. So again, notice with the notation here that we have the right-sided limit goes to infinity, and we have the left-sided limit goes to 0, and they don't equal. So here are the next lecture work questions, 3, 4, and 5. From this data table, what is x approaching? Is it approaching from the left or the right? And what number is the function going to? Well, if we look at the inputs here, we can see the 9s are starting to stack up. getting closer and closer to 6. For question 3. Now these numbers are always less than 6. Since they're always less than 6, it means they're coming from the left. And looking at the outputs, stacking on the 9s here, getting closer and closer to 11. So try this next data set out for 6, 7, and 8. So looking at the inputs, we're getting closer and closer to 10. Now these numbers here are always larger than 10. So we're coming to 10 from the right, approaching it from the right. Our numbers are always larger. And if we look at the outputs, we can see we got a bunch of zeros stacking in here now, and this is getting closer and closer to 0. So this leads us with these two approaches, so approaching from the left and approaching from the right. These are one-sided limits. And the other type we have is a two-sided limit. It's only this type here. And a two-sided limit, notice the two-sided limit has no superscript here. And if there's no superscript, then that means it approaches from the left and the right. And we can write this mathematically that the two-sided limit is defined when the left and the right equal. So in other words, if these equal, then we have a two-sided limit. So if we look at this example again, we saw just a few moments ago, we can see here the left and the right, and they don't equal. If they don't equal, there's no two-sided limit. And again, this comes from this statement. The left and right have to equal. And if they do, then we have a two-sided limit. That's not the case here, though. And so we would write this then as DNE does not exist. This two-sided limit does not exist. However, the one-sided limits do, though. Now, there is one more thing I want to say here, and it has to do with the difference between MAT213, which is brief calculus, and MAT221, which is the calculus more for the science and engineering. In 221, you learn more of the deeper logic that's putting these things together, these ideas. Where in 213, we don't go into that. But I want you to understand that there is a deeper setup to this that's all written mathematically that describes this limit. And in Math 221, they learn this as the precise definition of the limit. And we don't have to learn this in 213, but I want you to understand there is a deeper logic that holds this together that we aren't going to talk about. And our primary goal here in 213 is to really be able to do calculus, have some understanding of the process that's happening. But overall, our goal is to get our answers and have some understanding of what's going on. So you don't need to know anything that's on here. Don't worry about that. Just trying to help lay out there that there is some deeper math there. So anyways, our summary for what we just all talked about here is the important thing we started off with is this idea of an infinite process. of getting closer and closer to a number. And that we call that then x approaches c, where c is whatever number. The next thing we saw was, well, with a number, we can approach that number from the left or the right. And we symbolize that with these superscripts for left and right. And this idea of approaching, where we're getting forever closer to a number, in a sense, we're going to plug this into a function now. So before you plugged a number into a function, now we're going to plug this entire new idea of approaching into a function. And that gets us to the limit. There are one-sided limits, approaching from the left, approaching from the right. There is a two-sided limit. That means approaching from both, no superscript. And finally, if the left and the right equal, then you have the two-sided limit. And that's what this math statement is saying down here. And that is our first lecture.